In this video, we'll continue to look at electricity. Now, we're moving on to the next section of the syllabus, which deals with electrical quantities. So, according to the syllabus, you should be able to cite examples of the conversion of electrical energy to other forms and vice versa. Apply the equation V equals W over Q. Apply the equation P equals IV. Discuss the importance of conserving electrical energy and the means of doing so. Now, before we get into these specific objectives, what we will do first is to basically go through a few of the common circuit symbols which will be used we're likely to see in circuits, right? Because of course, electricity at this level, in most cases, you'll be dealing with a lot of circuits. And of course, you'll have to be familiar with a lot of these circuit symbols. So I will go through a few of the circuit symbols that you're likely to see in these electrical circuits. Now, you'd have met a few of these already. So, for instance, we have this one. This, of course, is a cell. So, a cell comprises a single long stroke and a single short stroke. Now, a battery is a group of cells. Right? So, no, this one's supposed to have one more. Right, so it starts there. 1, 2, let's stop it there. So, this is basically a battery, which is a group of cells. Right? And of course, it's not uncommon for you to see, well, you might see a plus sign, a minus sign there to indicate that this is the end with the higher polarity. This is a positive, the minus. Likewise, this is a positive and the minus. As I said before, the long stroke represents a positive terminal, the terminal at the higher polarity, and the short one, the negative terminal, right? We can have a switch. This, of course, would be an open switch. And if the switch is closed, it generally looks something like this. Right, so that's open and closed switch. Let me see what other symbols are quite common. If you see a circle with an A inside, this of course is an ammeter. An ammeter is used to measure current, right? Usually, if you see an ammeter, in many cases you may see a circle with a V inside. This of course is a voltmeter. And of course, a voltmeter is used to measure voltage or potential difference across a particular device, right? So those are some common symbols. Let me see what else you're likely to see. You may see a resistor. Now, a resistor may come with different symbols. So this is what we call a fixed resistor. You may see like that, or you may see a... Right? So both of these are what we call fixed resistors. So these, of course, are resistors of fixed resistances, right? While you have fixed resistors, you may have also what we call Weber resistor. A Weber resistor, same symbol basically, but you have an arrow stretching across it like this. So this, of course, is a Weber resistor. Right? Let me see what else. We can also a fuse. So this is a fuse. Now, the fuse has two symbols. One may look like this, or it may resemble a resistor, but the difference between the fuse and the resistor is that the line goes straight through. So either of these could be used to represent a fuse. Now, essentially, a fuse is a safety device which is used in a circuit so as to prevent too large a current from flowing. The fuse basically usually consists of a thin piece of metal. So when the current gets too high, essentially the melting point of the metal is reached, the metal melts and basically causes a break in the circuit, right? That is basically how a fuse works. And of course, each fuse would normally come with a particular fuse rating. That is the maximum current which basically the fuse will tend to allow to flow. If the current is aiming to exceed that value, then of course the thin piece of metal will melt and break the circuit, right? The fuse has a similar operation to a circuit breaker, right? So those are some of the more common symbols that we will actually encounter. Let's put a few more. We may see what is called a filament lamp. Filament lamp again. So this is a filament lamp. Now, in many cases, even though this represents a filament lamp, you may also see this, but even though this represents a different kind of lamp, this is supposed to be used like an indicator or a display, a signal lamp or indicator. But in some cases, some books may use them interchangeably, even though they're not exactly the same thing. All right, so those are the two symbols that you commonly see used for lamps. Earlier we mentioned semiconductor diode, so we'll just put that as well. This is the semiconductor diode, a little triangle with a little stroke at the end. So this is a semiconductor diode, or just a diode for short. All right. So once again, those are some of the more common circuit symbols that you're likely to encounter. And of course, if there's any other that you will encounter or you'll need to know, we'll basically look at those later on. So having looked at that now, let's now focus on what the specific objectives of this syllabus are. Right? Because of course, based on what the objectives required, we would have needed to mention some of these devices. And of course, we may just draw a few circuits, including them. So let's take these off. Now, according to the syllabus, we're supposed to be able to cite examples of the conversion of electrical energy to other forms and vice versa. Now, when you looked at mechanics, you would have examined the principle of conservation of energy. And according to the principle of conservation of energy, energy can neither be created nor destroyed, but can only be converted from one form into another, right? So what this basically means is that we can't, there's a fixed amount of energy in the universe. We can't add any to it, and we can't take any away from it. All we can do basically is to convert that energy from one form into another, right? Now, a battery is a source of electrical energy. Batteries, so let me just jot it down here. So we can talk about batteries, dynamos of an E. So dynamos. Generators. I mean, technically a dynamo is a form of a generator, right? Now, what do these devices have in common? These devices basically, they convert some other form of energy into electrical energy, right? So a battery will convert chemical energy into electrical energy. A dynamo will basically convert mechanical energy, and in particular kinetic energy, into electrical energy. And a generator will essentially use, for instance, chemical energy from some fuel, could be a diesel or gas, and eventually will convert that into electrical energy, right? So basically, these devices which convert other forms of energy into electrical energy, they are referred to as sources. Right? So they're basically sources of electrical energy as they convert other forms of energy into electrical energy, right? And of course, throughout our look at circuits, we will usually see at least one of these in our circuits. So we may either see, well, generally at this level, we'll see batteries, right? But of course, later on, we may see AC supplies, and of course, those of course will be converting other forms of energy into electrical energy as well. Right? For the most part, we'll definitely see batteries in our circuits, right? So these, as I said, convert other forms of energy into electrical energy. Now, while they do that, there are other devices in the circuit which, of course, do the reverse. They convert other forms of energy, or they convert electrical energy into other forms of energy, right? Now, let's see if we have any such of those devices. Let me just put back this one right here. We can put back the lamp. Right, we can put back the lamps, as we can clearly imagine what type of energy will be converted, or a lamp will convert electrical energy to, right? So lamps, of course, produce light. So they give off light, which basically means that the lamps will convert electrical energy into light energy, right? Now, generally, of course, whenever there's a lamp on, there's usually some amount of heat being generated as well. So therefore, we can see that lamps will convert electrical energy into light energy, because that is the primary form of energy that is really converted to. But of course, there's also some amount of heat given off, and of course, if you listen closely enough, you can probably hear some little buzzing, and so therefore there is some amount of sound energy being given off as well, right? Resistors, which we shall look at in greater detail later on, they also produce some amount of heat, and so therefore we can say that resistors basically convert electrical energy into heat energy, right? In terms of other electrical devices, we may have a buzzer or a bell, right? So we may have a buzzer or a bell, which of course is able to convert electrical energy into sound energy. And there's also a form of diode called an LED, which of course is able to convert electrical energy into light energy, right? So an LED stands for light emitting diode, and it is basically a diode which basically gives off light, and so basically it would convert electrical energy into light energy, right? So generally, devices which convert electrical energy into other forms of energy are generally referred to as let me not mention that, right? So as I said, we know sources, they convert other forms of energy into electrical energy, and of course other circuit components, they will do the reverse. All right, so having said that, we can take these off. Now, the syllabus wants us to be able to use this equation, or to apply the equation V equals W over Q. Now, basically, as I mentioned before, energy conversion takes place in electrical circuits. So, for instance, a battery will be converting chemical energy to electrical energy, right? So, a battery will be converting chemical energy to electrical energy, right? And as we mentioned before as well, a dynamo, which is also a source, will be converting kinetic energy to electrical energy. So these devices, which basically convert other forms of energy to electrical energy, are called sources, right? And basically, when this energy conversion is taking place, the amount of energy converted per coulomb of charge is said to be the no, that is not on the syllabus. Let me not mention that. Anyways, whenever devices convert other forms of energy into electrical energy, we use a term called the EMF to refer to these devices. So for instance, suppose we have a 1.5 volt battery, right? A 1.5 volt battery. Then this value of 1.5 volts is said to be the EMF. So the EMF E of the battery equals 1.5 volts. Now the syllabus doesn't require, knowledge of the use of this term. However, it is good to mention it, right? So this is said to be the EMF of the battery. Now EMF, of course, stands for electromotive force, but we're not going to go into too much detail in this in terms of this expression, right? So basically, what you need to understand is this: that devices which convert other forms of energy into electrical energy are referred to as sources, and this whole energy conversion is usually summed up in an expression called the EMF of that particular source. So for instance, you could have a 1.5 volt battery, and because it is a source, we would say that this is the EMF of the battery, right? Now, in terms of this equation, V equals W over Q, that equation is often used in terms of other devices which of course convert electrical energy into other forms of energy, right? So let's say, for instance, we have, say, let's say we have a lamp. We have a lamp, right? And this lamp is going to be converting, say, electrical energy to, let's just stick to the primary conversion, which of course is light energy. We know that there's going to be some amount of heat as well, but let's just focus on the primary conversion, right? Electrical energy into light energy. So in this equation, W represents the amount of energy converted from electrical energy to other form, right? So W will basically be the amount of electrical energy converted to other forms of energy, and Q represents the quantity of charge flowing. So therefore, this equation, V equals W over Q. V right here is said to be the voltage or the potential difference. So the potential difference, and the short form of potential difference is just PD across the device. So what this basically means is that if a lamp converts W joules of electrical energy into light energy or other forms, when there's a quantity of charge Q flowing through that device, then it means the potential difference or the voltage or the PD across that device is given by the formula V equals W over Q. So once again, this formula is used to give the voltage or the potential difference across a particular device when W joules of electrical energy is converted to other forms of energy in that device or by that device. So if we talk about, for instance, like a resistor would basically convert the electrical energy, let's say, into heat, right? So and we can talk about the potential difference or the voltage across any device in a circuit, any device which basically converts electrical energy into other forms, right? So let's just do a quick little calculation. Suppose, so let's say, calculate the PD across a device, let me put across a, let me just put a device. Across a device which converts 20 joules of electrical energy into other forms when 5 coulombs of charge flow through it. Right? So this is just a make-up question. So it says calculate the PD across a device which converts 20 joules of electrical energy into other forms when 5 coulombs of charge flow through it. So let's just write the information that we have. We have the energy converted, W is equal to 20 joules. We have the charge flowing, Q is equal to 5 coulombs, right? So the energy converted, W, is 20 joules. The charge flowing, Q, is equal to 5 coulombs, and therefore put it PD, V, equals W over Q, which gives us 20 joules divided by 5 coulombs. Now 20 divided by 5, that gives us 4, and the units of course will be joule divided by coulomb, or simply joule per coulomb, right? So the joule per coulomb is easily accepted as the unit of potential difference or voltage. But of course it is far more common to see the volt as the potential difference or the unit of potential difference, right? So we can write this as 4 joules per coulomb, or we may write it as 4 volts. And what this basically means is that 1 joule per coulomb is equivalent to 1 volt, right? So basically what this is saying is that when 1 joule of electrical energy has been converted to other forms of energy, when 1 coulomb of charge flows through a device, then the potential difference across that device is equivalent to 1 volt, right? So let me say that again, or we can say it another way. we could say that 1 volt is the potential difference across a device when 1 joule of electrical energy is converted to other forms when 1 coulomb of charge flows through that device, right? So the syllabus, of course, would have required us to use that equation, but it also basically makes mention of the definition of the terms and their units, right? So in this equation, of course, the V represents the potential difference or the voltage or the PD. W is the amount of energy converted from electrical energy into other forms, and of course Q is the quantity of charge. Would have already met charge, and the unit of which is a coulomb, and of course would have met energy, unit of which is a joule from before, and of course now we're being introduced to potential difference or PD, the unit of which is the volt, right? So having done that, let's just now move on to the next objective. So we know about energy, and we know that basically machines are basically any device which converts energy from one form into another, right? The rate at which machines do this conversion is referred to as the power of the device, right? So usually we can say that power, P, is equal to work done or energy converted So work done or energy converted divided by time taken, right? So using the symbols, we can then say P equals W over T. Good? However, if we take this equation, if we look at that equation there, we can say that V is equal to W over Q. And from this equation, it would therefore mean that W is equal to QV, right? So this equation, as given by the syllabus, is the equation which converts PD in terms of dividing the energy converted by the charge flowing. So V is equal to W over Q, which means that W is equal to QV. But of course, if you recall, we would have met an equation for Q, right? But of course, we can say that Q is equal to IT. And therefore, this means that W is equal to ITV. And if we therefore take this and substitute for W into this equation, we therefore get that P is equal to ITV divided by T. The T's cancel, and therefore get that P is equal to IV. And what this basically shows is that electrical power, and of course we're talking about electricity, so this is electrical power. Electrical power is simply equal to current times voltage, right? So electrical power is equal to current times voltage. Now, of course, look at mechanics, we have already met power, and we know the unit of power is the joule per second or the watt. However, if you look at the right-hand side of this equation, current times voltage is giving us power. The SI unit of current is the ampere, and the SI unit of voltage or PD is the volt. So what this basically is showing us is that in this case, 1 watt is equivalent to 1 ampere times 1 volt, right? So using this formula, P is equal to IV, the SI unit of power is the watt, the SI unit of electric current is the ampere, and the SI unit of voltage or potential difference is the volt. And therefore what this means is that 1 watt is equivalent to 1 ampere times 1 volt. So whenever we're using this equation to calculate power, we don't need to write down ampere volt, we can just write down the unit as watt, because of course you know that this will be equivalent to the watt. The last requirement of the syllabus wants us to discuss the importance of conserving electrical energy and the means of doing so. Now, we mentioned before the principle of conservation of energy, and according to the principle of conservation of energy, energy can neither be created nor destroyed, but can only be converted from one form into another. Now, when this objective of the syllabus refers to energy conservation or conserving electrical energy, it is not talking about the principle of conservation of energy. It is basically referring to the avoidance of wasting electrical energy, right? So usually, I mean, in real life, forget about physics for a while, when we speak about conserving things, we basically use that word to mean not to waste them, right? So we're often told, you know, to conserve the water. So turn off the pipe if you're brushing your teeth, don't just leave the pipe running, don't take excessively long showers and so on, right? So the word conserve in that context is basically means not to waste. So when they basically talk about the importance of conserving electrical energy and the means of doing so, they're basically talking about means by which electrical energy can be saved or avoided, or we can avoid wasting it, right? And of course, there are common instances in which you can avoid wasting energy. Some of which include basically turning off electrical devices when they're not in use. That is probably the most common one. So if you're home alone, there's no need to basically have all the lights in the house turn on at the same time, right? There's no need to have the AC unit running if there's nobody in the room using the AC unit. There's no need to have both the TV and the radio running at the same time if you're only watching TV or if you're not paying attention to any of them, right? So those are basically commonly known measures by which you can conserve energy, right? However, we can also take more steps into conserving energy. For instance, we can actually conserve energy by using energy efficient light bulbs. So we can actually replace our incandescent bulbs, and incandescent bulbs are the regular bulbs with the filament, and of course those tend to get very, very hot, and because they tend to get very, very hot, they're not very efficient. So they would probably waste a good probably 70% of the electrical energy supplied to them. So it means that they're basically roughly about 30% efficient, as 70% of the electrical energy, or could be more, somewhere around there, would be lost as heat. So basically, one way of conserving energy is to basically replace our incandescent bulbs by LEDs or LED bulbs or fluorescent lamps, right? CFLs, compact fluorescent lamps, right? So that will basically reduce the amount of energy that is actually wasted, and of course should have a positive effect on the electricity bill as well, right? So these bulbs are far more efficient. One, they actually use less electrical power, and they basically convert more of that into useful energy output or useful power output in the form of light. So as a matter of fact, basically, if I'm not mistaken, I think a 13 watt compact CFL or compact fluorescent lamp would be equivalent to about a 60 watt incandescent bulb. All right. Right. So that number may vary actually from manufacturer. So what I do have here, however, is an LED bulb made by Philips, and on the box, this is basically an 8 watt LED bulb, and it's basically saying that it is equivalent to a 60 watt incandescent bulb, right? So over time, this would result in significant savings, especially if you live in a big house where you have a lot of these bulbs in different rooms, right? So that is basically another way in which you can actually conserve energy. There are other ways of conserving energy. I mean, the regular ways, don't go in your refrigerator every 5 minutes. If you're basically making a cup of tea, then there's no need to actually fill the kettle, right? And so on, right? So these are just some ways in which energy can be conserved. Of course, you know that in most countries, electricity is generated from the use of fossil fuels. Now, fossil fuels, of course, are not replenishable, right? Or in the more you use, how do I say this? They're not renewable then. In other words, then they do take a long time to form, and of course generally the rate at which they're actually being depleted is much greater than the rate at which they can actually form, right? So of course many countries are now looking into renewable energy in the form of, you know, wind, solar, and so on. Of course, two of which are quite common in this region. Right, so we've more or less basically looked at the requirements of this section of the syllabus. We're able to talk about energy being converted from electrical to other forms and vice versa. And of course, apply the equation V equals W over Q. We looked at the derivation of the equation P equals IV. Now, bear in mind, the syllabus does not require you to derive this equation, but of course, I went through the derivation to show you how the equation came about. And of course, we were able to discuss the importance of conserving electrical energy and the means of doing so.